change, if I have a coordinate change, with coordinate change mapping, we looked at one of those today, like you trade xy for r theta, that's coordinate change. So coordinate change is a mapping from R2 to R2, or from R3 to R3, through same inputs as outputs. Well, the derivative in that case is actually a 3 by 3 matrix if we're going from R3 to R3. And we will need to look at that, actually, as we study integration going on. So here's some explicit examples. Like the, oh, come on, seriously? So for example, if I have the space curve tt squared sine 10t, the linearization at t equals to 1 is L of 1 plus h is that, which is just this. That's a parameterization of the tangent line. That is the linearization of the space curve. And right here, this one won't be familiar yet, but it will soon be familiar because we're going to be talking all about tangent planes coming up. But right here, if you look at z equals to x squared plus y squared, that's a paraboloid, right? We've talked about that. At 1, 2, this equation right here is the best linear approximation to the paraboloid. Come on, is this for real? I didn't even touch it. You know, all right. Here's some pictures. All right. Now, right here, we have like a curved space, right? And that line under, this under here, right, that would be the tangent plane. That's a normal line to the tangent plane. We'd like to understand how to find this tangent plane for a given graph or level surface, right? How do you do that? How do you find the tangent plane? That's something we will answer here shortly. Here's another picture, tangent plane, normal line. Starting system, what on earth is this? I tell you what, well, all right, there we go. So, natural question to ask is, what's the connection between this Fouché derivative that I just talked about and like the derivative in sense of calculus 1? So number one is, they're the same idea. This calculation here, which you can just loosely read through if you want. If you're not interested, that's okay. If you're really interested, come take advanced calculus from me. I will explain it more there. But it's in full agreement with what we did in calculus 1, in fact. And let me go on here. Here's a technical example we can skip past. Here's a theorem. If you have a function that's differentiable from Rn to Rm, guess what? It's continuous. So differentiable implies continuous in the general derivative. If you have that the function's differentiable, then all of the directional derivatives exist. So like if you know that the function's big derivative exists, then all of the little directional derivatives exist. But what's a little bit nefarious is that it's possible for a function to have all of the directional derivatives exist, and yet this general derivative doesn't exist. Now, the general derivative existing essentially is tantamount to there being a well-defined tangent plane to the object. Like if there's not a tangent plane to the object, the function's not differentiable. It's possible to have directional derivatives in all different directions existing, and yet somehow the tangent plane fails to exist. So like, let's see if I can show you. This is sort of the standard example, annoying example. This is a function, this is just a one-dimensional thing, but this is a function which has a derivative which exists at 0, and yet it is not continuously differentiable. Like the derivative itself is not it's not continuous. And so like it has technically it has a tangent line there, but it's not a good approximation to the function. So some people would say the tangent line doesn't exist there. I guess there's kind of a point of debate there. All right. Sorry, let me zoom out a bit here. I'm trying to get to a point. So let's say this. The tangent plane to a graph, we'll take this as a reasonable sort of intermediate definition. The tangent plane to a graph is formed by the union of all possible tangent vectors to curves, where we have, a smooth curve on whatever, like the surface we're talking about. All right? If these vectors do not form a two-dimensional plane, then the tangent plane fails to exist. So, in short, the tangent plane is the graph of the linearization. And so here's some annoying examples where, anyway, if you read the notes, I have some examples where the tangent plane doesn't exist, all right? But here's the interesting thing. If you have a function of several variables and you compose them, all right, then you can talk about the chain rule for that. And it turns out that, like, if I take the derivative of the composite of two maps, it turns out that, like, the derivative is the derivative of the composite is actually the composite of the derivatives. And what that means for the matrix is that, like, the matrix of the composite is related by, it's the matrix of the first one multiplied by the matrix of the second one. And this matrix formula produces all of the chain rules that we see in this course, every last one of them. And here's how that goes. Well, this is the proof of the chain rule, but we don't care about that so much. Here's one. So if I'm looking at the coordinate change map, so I go from R2 to R2 with x here, let's see here if I could see it. So if I do this times that matrix, I get the chain rules I wrote today. And this matrix is exactly the matrix of the coordinate change map as I have up there. So, like, you get partial x, partial r for the first column, partial x, partial theta for the second column, like that. Let's see, I think I have another example we can look at. Oh man. Rats. Thought I had another example. Right, anyway, so any questions? I mean, I don't know if I have explained anything today, really. So. All right, so let me tell you about where we're going to. We're about to start talking about how to take partial derivatives of functions which are really I'm about to talk to you about how to take partial derivatives of equations. So far I've mostly focused on partial derivatives of functions, but you can then start asking questions like, how would you take a partial derivative of an equation where maybe you don't know what the which is the independent variable, let's say something like that. So example, this is 5, isn't it? So what if you have something like w x y z equals to 1? All right. So my question then is, which one's the independent and which one's the dependent variable here? Whatever I want is a very good answer. And how would I find the partial derivatives of whatever I want in terms of the other ones? Check this out. So the calculational principle is simply this. You can take the total differential of the expression, and from that you can derive whatever partial derivatives that you want. So like here, if I take the total differential of this, I get x, y, z dw plus w, y, z dx plus x plus wxz dy plus wxy dz, that equals to 0, right? So you pick whichever one you want. So Violet, which would you like it to be the dependent variable? You have 4 choices. Z, you want to choose z to be the dependent. So solve for dz. dz is equal to minus xyz dw minus wyz dx minus wxz dy, all divided by, what was the coefficient of dz? wxy, right? And if we simplify that, how's that go? What cancels? There's some cancellation, right? The x's cancel, the y's cancel. We're left with what? Minus z over w, is it? You guys tell me if I'm right or wrong. And what's here? Y's cancel, w cancels. Z over w? No, just z? Z over x, right? dx minus, if I can do the canceling, z over y dy. This right here is what I would say is partial z, partial w, holding x and y fixed. This right here with the minus is partial z, partial x, while holding w and y fixed. This right here is partial z, partial y, while holding w and x fixed. So this notation is new. We'll talk more about it as we go on here. But and you won't find this notation in Stewart. This is one of the principal shortcomings of Stewart in terms of partial differentiation, is he doesn't talk about this hardly at all. But this notation declares to the reader that I'm using these as my independent variables, right? So we should try to think about this more. But there it is. Like, as a calculational method, it's very simple. You just solve for the differential you're interested in. That reveals the partial derivatives as the coefficients of whatever the remaining differentials are. This is a general calculational principle. Anyway, I should shut up.